Hello everyone, my name is Deanne Coppejans and I'm a postdoc at Northwestern University. So I'm going to give you a review today on observational studies of jets in galactic accreting compact objects. Now over the past few years there have been a lot of improvements in telescope sensitivity, multi-wavelength coordination and timing resolution, which has enabled a lot of advancements in our understanding of the core jet physics. I'm going to talk about some of those today. So galactic accreting compact binaries come in a range of different forms, spanning white dwarfs, neutron stars, and black holes, and their accretion occurs via a number of different processes. So there are a number of different questions we have about the jets in these objects. For example, how are they launched and collimated, and how does this change as a function of accretor class from low magnetic field systems right through to rapidly rotating compact objects? And there are a lot of different techniques we use to answer these questions about jets. For example, high resolution radio observations of the jets through to timing studies across multiple wavelengths. So there's a number of reasons that we need to understand jets. They remove angular momentum, energy, and mass from systems, and they put this into the environment, and they help accelerate particles. So they're of much broader astrophysical importance. So I'm going to start with a brief introduction to the terminology I'll be using in this talk. So in the top right corner, you'll see an illustration of an X-ray binary. It consists of a few main components. Firstly, there's the secondary star that's feeding mass onto the accretor. And then there's an accretion disk that emits at the soft X-ray wavelengths. The matter moves down through this disk and then through the inner accretion zone where you have the corona that produces hard X-ray emission. Then you have the jet, and we typically see that at radio wavelengths. Now, in X-ray binaries and a number of accreting compact objects, you have an instability in the accretion disk. So matter is piling in from the secondary star, and at some point the density reaches a point where it triggers a disk instability. And the accretion rate through the disk increases and the whole system brightens. So if we look at this diagram called a Q diagram, where you have the X-ray luminosity on the y-axis and the X-ray hardness on the x-axis, we start with the system down in a low luminosity state. As it enters outbursts and the luminosity and mass transfer rate increase, we move to point B, and it remains in this bright outburst state for a while, and then it decreases down to quiescence again. So this is a reason why we move in X-ray luminosity. Now, the disk and the X-ray corona produce X-ray emission that's respectively soft and hard. So you move across this diagram because of the different components involved. So in this hard part of the diagram, you have the corona dominating, and then the left part, you have the soft disk emission dominating. So X-ray binaries move through this system of states. Now, interestingly, we also know that you observe different kinds of outflows. There are different outflows associated with the different states. So in the hard state, you get a continuous, steady, compact jet, as shown in this illustration down here. But as you move through to the soft state, past point C, this core jet is quenched to some degree, and you get ballistic discrete ejections that are optically thin. We call this the transient jet. Anyway, as the system moves down back to quiescence, the core jet reestablishes itself, and we wind back at point A. So this is a general picture. Okay, I'm now going to proceed to tell you some recent results involving black holes, neutron stars, and white dwarfs. So starting with the black holes, one of our questions is, how are the jets affected by the dynamics of the inner accretion flow? This is particularly relevant and interesting if you consider the case where a black hole has a spin axis that's not aligned to the orbital plane of the X-ray binary. In this case, because you've got a rapidly spinning massive black hole, general relativistic effects come into play, and you get frame dragging or lens-thirring precession of the inner accretion disk, and that actually makes a warping of the inner accretion disk, as you can see in this diagram here. So what happens with the jet in these circumstances? So Miller-Jones et al. 2019 looked at this in detail through X-ray and radio observations of the accreting black hole V404 Cygni in outburst. And they found something really interesting. So if you look at the bottom panels, this is high resolution radio observations. And at the center of the cross is the core of the jet. And this precession of images show it moving into the soft state. And what's interesting is you see that the core jet is quenched over time and that there are these discrete ejecta as we'd expect. But interestingly, the orientation of these discrete ejecta change over time. So what you're seeing here is the angle of the jet changing over time. You can see that even more clearly in this video. This is just a time series where you see the discrete ejecta moving over time. Now, they argue that this system probably received a natal kick when it was formed. So it's likely that the spin axis of the jet and the orbital plane are offset. And based on the X-ray observations, they argue that there's likely lens-thirring precession happening in V404 Cygni. So the conclusion is that we likely have lens-thirring precession. And if you have a changing precessing in a disk, then depending on which model you invoke to launch the jets, whether you use magnetic field lines in the jets or outflows, you'd naturally expect the jet to change orientation over time. So this was a really exciting result showing that you get an interplay between the jet precession angle and the inner disk. Moving more on to further VLBI images of black hole jets. This was a result by Bright et al. 2020 looking at core jet quenching and the discrete ejecta from MAXI J1820 plus 70. So they ran a radio campaign on the secreting black hole over 200 days. And what they found is they actually detected radio emission in the soft state. Now, in the soft state, the core jet should be quenched. So first it was confusing what this emission came from. But using VLBI, they found, as I'll show you in this bottom left-hand corner, they found that the core jet was quenched, but it had ejected these discrete ejecta that were expanding ballistically. So here the solid line indicates where the core of the jet should be. And here are these blobs of apparently superluminally moving ejecta blobs over time. So this was 3 to 23 days. At later times from 90 to 200 days, you can see the continued movement of these ejecta, and you can see them brightening and fading in radio as they interact with the surrounding CSM. So this was the first clear observations of the full quenching process. Moving on to neutron star systems. So one of the outstanding questions in the field is whether the highly magnetic accreting neutron stars can launch jets. It was previously believed that neutron stars with magnetic fields over 10 to the 12 Gauss could not launch jets. So observationally, this idea came about because they were not detected at radio wavelengths until very recently, that is. And theoretically, there's an expectation that they can't launch jets because there essentially isn't an inner accretion disk in these systems. So there's an outer accretion disk, but at a certain point, the magnetic field is so strong that it channels material from the disk onto the field lines and down onto the neutron star. You can see an illustration of this here. So one of the key models for jet launching in neutron star systems invokes the magnetic fields in the inner accretion disk to help launch jets. And that wouldn't be possible in these systems. But then in 2018, two highly magnetic neutron star accretors were detected at radio wavelengths, HER-X1 and GX1+4. And the finding of these was that the radio emission is potentially from a jet. Then later on that year, Van den Eyden et al. Observed Swift, or published Swift JO243 plus 6124. This is a highly magnetic accreting neutron star as well. And their X-ray and radio observations they found indicated a jet in this magnetic system. So let's look at these results in a bit more detail. Here you'll see an X-ray light curve in gray with the radio observations at two different frequencies shown in red and blue. And now the key thing is that the radio emission is correlated with the X-ray emission. As it decreases, so does the radio emission. And what's more is that these are related or correlated in a way that is consistent with other neutron star and X-ray and black hole X-ray binaries. Another thing is that the linear polarization was less than 15% over the course of the outburst. And finally, the spectral index of the radio observations went from negative numbers and flattened out later in the outburst. So let's look again at this Q diagram. So they found that this evolution in the radio spectral index is consistent with the scenario where we start at the peak of outburst point C with an optically thin discrete ejector. And over time, the core of the radio jet reestablishes itself as we move down to quiescence. And we once again get a flat to inverted radio spectral index from a compact jet. Now, they looked at a number of alternate scenarios for the radio emission, and they ruled out all those scenarios and found that this emission is consistent with a jet. So this is the first time we've seen a jet in a highly magnetic accreting neutron star. Now, this has a number of interesting implications. The first of which is that since there's no inner accretion disk, you would need the jet to be launched from the disk at much larger radii, in this case greater than 320 gravitational radii. Now, the inner accretion region is also extremely different to other classes of neutron star accretors, yet we get a similar evolution of the radio and X-ray emission. So it's not clear what effect the spin rate and the magnetic field strength of the neutron star are to jet launching in these systems. Now, moving on to the white dwarfs, jets have been found in most classes of accreting white dwarf binaries, but there was until recently one key exception. It was until recently thought that cataclysmic variables could not launch jets. These are white dwarfs that have a low mass main sequence star secondary that accrete via Roche overflow. And it's a very similar story to the magnetic neutron stars. They weren't detected at radio wavelengths, which led to the conclusion that they weren't launching jets. Now, there were a few implications because of this. Firstly, CVs have been used to constrain jet launching models in other classes of compact accretors under the assumption that they don't launch jets. Secondly, if CVs are actually launching jets, then they're a very interesting target because they have very well constrained distances, and that would allow us to more easily determine the jet properties based on observations. Then they're also non-relativistic, and they're coming in a range of different properties, so they would be very interesting targets for constraining jet launching physics. So in 2008, Accreting et al. Compared the outbursts of cataclysmic variables to X-ray binaries. Now, they have the same outburst mechanism and they show similar phenomenology. So in theory, they could be moving through the same accretion states. The key difference here is that the disks in CVs emitted optical wavelengths, not X-rays, and the inner accretion flow emits at EUV or X-rays. So to to do a like-for-like comparison with the X-ray binaries, Curtin et al. Reasoned you should be comparing the EUV X-ray emission to the optical emission. And there's one CV where we have a full outburst in these three wavelengths, and that was SS Cygni. So Curtin et al. Took this data and they compared it to the X-ray binaries, and sure enough, they found that if you plot the optical luminosity as a function of the fraction of the X-ray to X-ray and EUV emission, you get the same movement through accretion states, or an analogous movement through the accretion states in the white dwarf accretors. So here's the white dwarf SS Cygni versus a neutron star in a black hole system. So in analogy, you'd expect a compact jet in quiescence and on the rise to outburst, and you'd expect radio flaring emission as the core of the jet was quenched as it moved to the soft state. So prediction is you should see a radio flare at this point in the diagram. And sure enough, when they looked at SS Cygni at radio wavelengths, this is what they detected. So here in gray is an optical outburst of SS Cygni, and the black points show this clear radio flare and the transition to the soft state, and then a drop off in the radio emission. So they detected this flare, and in follow-up observations of other outbursts, they repeatedly detected this flare at the same stage of the outburst. What's more is in 2016, Russell et al. Found a 4 sigma detection of extended radio emission, but it was not conclusive what was the nature of that. So all these studies have found that this radio emission in SS Cygni is best explained by synchrotron emission from a transient jet. But what about the rest of the population? Well, it's recently been discovered that non-magnetic CVs are indeed significant radio emissions. So the population are emitting significant radio emission. It was just due to lack of sensitivity that we didn't detect them before. So the properties of this radio emission are consistent with the jet model, with similar luminosities and variability timescales to SS Cygni, and the radio emission is dependent on the outburst state. But one key thing is that we have not yet detected the initial radio flare. So here we show the optical light curve in gray, with the radio light curves of SS Cygni and open points, and the close points show a bunch of other CVs in outbursts. And we don't see this corresponding flare in any of these systems, but unfortunately the timing was not enough to rule it out. So I've just discussed the arguments for jet launching in CVs, but there are also a bunch of open questions about this interpretation. Firstly, why is there persistent radio emission in the equivalent of the soft state? Now, we do occasionally see some X-ray binaries with persistent radio emission in the soft state as well. Secondly, there's some outbursts of SS Cygni, anomalous outbursts that show flaring that we can't ascribe to this model. And there are also some non-detections of nearby CVs in outburst and some potential alternate emission mechanisms that we need to explore further. So please see Coppejans and Knigge, Coppejans and Knigge 2020 for a review of this. But the one point I am going to discuss is whether the hysteresis is actually comparable to the X-ray binaries. So Hamari et al. Argued that in CVs, this mapping maps the outer disk to the very inner disk, whereas in X-ray binaries, you're only comparing the emission in the very inner region. So in CVs, you can naturally expect this hysteresis and fully explain it using the disk instability model. But in the X-ray binaries, because you're invoking the corona, you can't explain it fully without the disk interaction model. So Hamari et al. Did compare the very inner accretion flow And as you can see in this diagram on the right, they found that comparing the X-ray and EUV luminosity over time, you can still get a hysteresis in CVs. But now the question is whether this hysteresis is analogous to the X-ray binaries. We need, in essence, we need a model-independent, resolved radio detection of a jet to conclusively determine whether CVs launch jets. So I've talked about a bunch of different discoveries in the last few years about jets in neutron star, white dwarf, and black hole systems. The improvements in sensitivity, time resolution, and multi-wavelength coordination have led to these advances and many others, but there's still many other outstanding questions about the detailed physics of jets and compact accretors. And future observational improvements will help us answer these. And I just want to end off on the note that comparative study between these different accretor classes are a very powerful tool to probe and constrain the jet physics. Thank you.